Greetings viewers, and welcome to the first lecture in a series to cover the subject of circuit analysis. Let's start with the topic of the electric charge. The unit for electric charge is the coulomb. The symbol for the coulomb is the capital letter C. The letter Q, capital as well as lowercase, is often used in formulas to represent charge. One proton has a charge of approximately 1.602 times 10 to the negative 19 coulombs, and an electron has a charge equal to the negative of that value. In other words, the negative 1.602 times 10 to the negative 19 coulombs. Now, that number is known as the elementary charge. So a proton has a charge equal to the elementary charge. The symbol for the elementary charge is the letter E in lowercase. I'll be using a red circle in this lecture to represent a proton and a yellow circle to represent an electron. Let's move on to current. The unit for current is the ampere. The symbol for the ampere is the capital letter A. The letter I, uppercase as well as lowercase, is often used in formulas to represent current. Current is defined as the rate at which positive electric charge passes through an arbitrarily chosen point of a conductor in an arbitrarily chosen direction. Let's break this definition down into bite-sized pieces so that we can understand it as a whole. First, we need a conductor. I've drawn this red rectangle to represent a conductor. Next, we need to have an arbitrarily chosen point. So this green line here is going to be my arbitrarily chosen point. Now you may say that's a line and not a point, and you're right, but try not to get caught up in the semantics and try and understand the concept that I'm trying to explain. Next, we need to have an arbitrarily chosen direction. I've chosen this direction to be to the right, represented by this yellow arrow. Now this is going to be the direction of the current. Next, we need positive electric charge, so we'll place some protons inside of this conductor. Next, we need to add some movement, since these charges are going to be passing through our arbitrarily chosen point, and they're going to be moving in the arbitrarily chosen direction, in other words, to the right. Finally, we need to look at the rate at which all of this is occurring. So, what we need to know is how much charge is passing through this point in a given amount of time. Let's say that amount of time is 1 second. Furthermore, let's say the amount of charge is 1 coulomb. So, we have 1 coulomb worth of charge passing through this point in 1 second. That would be 1 ampere. So 1 ampere is the equivalent of 1 coulomb of charge passing through a point in 1 second. Now we have a positive value for this ampere since the positive charge is moving in the chosen direction. What if the positive charge was moving opposite of the chosen direction? Well, then that would be negative current. So if we chose the current to be to the right, then we would have to represent that current with a negative number. Well, what if the charges were negative and they were moving in the direction that we chose? Well, that would also be negative current. So if we chose the current to be towards the right and the negative charges were also moving towards the right, then we would have to represent that current with a negative number. Furthermore, if those negative charges were to be moving opposite to the chosen direction, then this would be positive current. And this is actually what happens in a conductor. The electrons, the negative charges, are actually what are moving inside of a conductor. However, this definition came about before that was really appreciated and understood. So when you see positive current moving to the right, you know that what's really happening is the negative charges are moving to the left. In general, the formula for current, instantaneous current, is given as the derivative of the charge with respect to time passing through a specific point. Now, in circuit diagrams, the conductor, in other words, the wire, is represented by a solid line, and the current is represented by an arrow. Let's move on to the concept of voltage. Now, the unit for voltage is the volt, and the symbol for the volt is the capital letter V. The letter V, capital as well as lowercase, is often used in formulas to represent voltage. So this can be a little bit confusing since the symbol for the unit as well as the symbol used for voltage in a formula is essentially the same. The voltage is the work that is required to move 1 coulomb of electric charge between 2 points. Let's try and understand this definition. Let's say that positive current is flowing from point 1 to point 2 through an electrical component. Let's also say that it takes 1 joule of work to move each coulomb of charge from point 1 to point 2. In this case, the voltage across point 1 and point 2 is 1 volt. This is also known as the potential difference between these 2 points. The electric potential of point 1 is greater than point 2 in this case since there's positive current from point 1 to point 2. Now, let's say we initially didn't know the direction of current, and we assumed electrical potential of point 1 was greater than point 2. So we put a plus sign at point 1 and a minus sign at point 2 to represent that the potential at point 1 is greater than the potential at point 2. To verify our assumption, we connected a voltmeter across the 2 points, and we discovered that point 2 actually has a greater potential than point 1. So what do? We can choose to keep the plus and minus signs as they are and express the voltage with a negative number. Or we can choose to reverse the plus and minus signs and express the voltage with a positive number.